When God created the universe, he started with light. Genesis chapter 1. Let there be light. From light came matter and us. Light sets the speed limit of the universe. It regulates time. And it gives us great insight into the universe around us. It holds great secrets. No scientist truly understands light. However, we do know the wave nature of light. Here is my summary. Outline. 2 videos. This video, a video of light. Let's make light. Light is an electromagnetic wave. Maxwell derives light from the great works of Gauss, Ampere, Faraday. The next video we'll get into photons in light and some other really cool stuff. It looks like we're looking at 2 charges, one positive, the other negative, moving in opposite directions. This is what happens in an antenna, and it's technically called an oscillating electric dipole. Yeah, the interesting thing about a dipole is it creates an electromagnetic wave. So how does it do that? Well, Maxwell demonstrated how this is done, or the fact that it is done, giving several physical phenomena, and I'll get to that in more detail here in a minute. But let's take a look at this picture. These are electric field lines right here. And if you draw a tangent line to each one of these curves, that provides you the direction of the electric field. Okay, so at this point here, the electric field is straight up. Okay, at this point here, the electric field is straight down. Now, in between here and here, the electric field will go to 0. So at a particular point in space, the electric field is going like this. It starts, say, in this direction up, then it comes back down, it goes to 0, and then it comes down and goes in the negative direction. So it is oscillating in this direction. The wave, the electric wave in this example, actually it's called the electromagnetic wave, is moving to the right. Okay, it's actually moving away. It's actually moving out in 3 dimensions, but at this particular point, it's moving to the right. Okay, so you also have a magnetic field which is changing, and since it is perpendicular to the electric field, which means it's at a 90-degree angle to the electric field, and it's also at a 90-degree angle to the direction of travel of the wave, again, which is to the right, if you're at this point here, then that means the magnetic field is coming out towards you. It's coming out of the screen and into the screen. So it's coming out, it gets to its maximum value, and then it retreats, goes back into the screen, becomes 0, and then goes back into the screen on the other side. Okay, so that's how an electromagnetic wave works. And again, it's all due to this moving or accelerating charge, which creates a disturbance in the electric field. Now, depending where you are relative to these moving charges, the electric field is going to be different. So here it's pointing up, this particular location. Here it's pointing down. If you change your position, then the direction is very different, right? If you're up here looking at it, electric field is in this direction, down, right? Electric field in this direction is in this direction. Here it's either up or down if you're at this point here. And I'll show you how we use plane waves to model electromagnetic waves or light at a particular point in space. So an equation I'm going to show you may be completely valid here, but it won't be valid anywhere else near this oscillating charge. So let's play this a little bit more. Pretty cool. Again, this only appears like the wave is moving to the left or right, but it's also it's moving spherically outwards. So it's moving out in all possible directions, somewhat like a ripple on a pond. You know, toss a stone into the water, into a pond, and you'll see these concentric circles or waves spread out from the source. So it's kind of similar, but not exactly that. It's not exactly a spherical wave. It's actually far more complex than that. Okay, so here's another perspective looking at the electric field depicted by these arrows. So at this point, the electric field is pointing in this direction, right? So again, what's the electric field? It's where a positive charge wants to go due to the presence of other charges. All right. So at this point, it wants to go away from this guy, right? And it wants to go towards this guy. So when you add those two together, then the net is this. Is what I'm doing now is I'm moving the charges closer together, trying to keep the yellow sensors in the middle. Okay, and as you can see, the electric field vector is changing. Okay, and I took a snapshot of that. And I'm going to do a couple of more configurations and take a couple more snapshots, and just to show you how this thing oscillates as this antenna or these charges move backwards and forwards. Excuse me, I'll show you why here in a second. But anyway, the electric field looks like this, right? It's going up, decreases in magnitude, it goes to zero at this point, then it flips and it goes down, and it does this back, it just does this as these charges oscillate at this particular point in time. Now here, it's doing the same thing, right? But at a little bit later time, right? Because it takes time for this information about the oscillating charges to get to this point. And this information travels at the speed of light. Okay, so essentially there's your wave, right? It's going to oscillate here. The electromagnetic wave is going to pass through here before it passes through here. Okay, so here is a electric field vector diagram that I created. And it just proves why the electric field vector is just going up and down. And from the simulation you saw, here's the electric field vector. All right, it points down when the charges are in this configuration. As the charges get closer together, it changes. Eventually it goes to zero once the charges are on top of each other. And once they flip directions, the electric field vector starts to point in this upward direction. Okay, so let's so at this point here in the electric field, if you were to put a positive test charge here, it'd want to go in this direction because of the negative, right? Positive attracts negative. And the positive want to go in this direction as a result of that one because positive repels positive. Okay, now if you add these vectors together, you'll see that the x components of this vector, which is this component over here and this component over here, that's in the negative direction, that's in the plus direction, they cancel. But their y components sum. Okay, so that's why you saw that at that particular point, the electric field was oscillating in this direction, right, as these charges were oscillating. And you'll see when I put a plane wave model at this point, its oscillation will be constant in the same direction. And this basically explains why. Okay, so you saw in the animations in the video that I was looking at the magnitude of the electric field at a particular point in time. It was just going up and down, up and down. And I demonstrated that that was due to the fact that the components of the E field vectors in the x direction were cancel, and only the vector components in the y direction were summed. So it was going up and down, up and down. So here is an equation that would be fitting, that would be accurate in modeling this electric field at this particular point. Okay, and as you can see, it's a cosine function, right? Here's the wave. Here's a cosine function. Peak to zero, peak back towards zero, just oscillates like this, like a wave, like this. Okay, so it is an appropriate equation. So what is all this stuff? This is the amplitude, the maximum value of the electric field. Okay, so that would be this right here. That's the maximum. And then as you can see, the cosine of this angle, right, varies between -1 and +1. Okay, so that's why it goes from a minus to a plus, and everywhere in between. Okay. And then okay, so the electric field's oscillating in this direction. The wave is moving in this direction. And the magnetic field, which is also perpendicular to the direction of the wave and also the electric field, is either coming out of you or going into the page. And I'll explain from Maxwell's equations where these equations come from. Okay, here is the electric field part of the light wave. Here is the magnetic field part of the light wave. Okay, so an image of this equation is right here. Okay, so here is the electric field. See how it's oscillating via a cosine function. Here is the angle kz minus omega t, and I'll talk in great length about this here in a minute. And it's oscillating in the x direction. So here's the x direction, and here's the B field. So it's a similar form. It's oscillating in the j direction, so out of the page and into the page. And again, the wave is traveling in the z direction, so it's a pretty good model. Here is an animation of an electromagnetic wave, light, moving. So using the coordinate system I was using, z would be into the page. See how it's moving into the page? It looks like the orange part, I'm calling this direction the x direction, so it's oscillating in the x direction, moving in the z direction. Okay, so that's the red part. And then the blue or kind of purplish part is oscillating. Okay, if this is x, that's z. It's oscillating in the y direction. Okay, so again, it's all perfect in terms of meeting the requirements of the mathematical of light and consistency with Maxwell's equations. Oscillating in the x direction, oscillating in the y direction, traveling in the z direction. Let's play it one more time. Pretty cool. So k is equal to the wave number, and it's equal to 2 pi over the wavelength. The wavelength is the distance. Let's say the wave starts here. So where does it repeat itself? It starts to repeat itself here. So this is the distance of the wavelength from here to here. Okay, and omega here looks like a W. Omega here is defined as 2 pi times the frequency, which is also equal to 2 pi over the period. The period is the time it takes for the wave to repeat itself. Okay, so if it's, how long does it take for it to go from here back to here, okay, where it starts again? So this time here is referred to as the period. So what I've done here is I've substituted 2 pi over lambda for k here, and 2 pi over t for omega here. So this equation becomes this equation. So as you can see, this equation, it repeats itself every 10 meters. So z is equal to 0, that's where it starts. That's this guy right here. Right, t is equal to 0, z is equal to 0, that's where it starts. And then say at 10 meters, right, 10 divided by 10 would be 1. So you have to pick a point t here, some value such that the wave has had a chance to pass a particular point in space. So every lambda, this wave will have had a chance to repeat itself. So this is just detail on how I compute the period. So once you establish the wavelength of the light, you immediately establish what the period of the wave is. So lambda times frequency is equal to 3 times 10 to the 8th meters per second. The period is defined as 1 over the frequency. So let's compute the period and the frequency for a 10-meter radio wave. Okay, so frequency is equal to the speed of light divided by the wavelength. 3 times 10 to the 8th meters per second divided by 10 is 3 times 10 to the 7th oscillations per second. So that's really remarkable. This thing's oscillating up and down, about 30 million times per second. So the period is the inverse of the frequency. That means the wave repeats itself every 3.33 times 10 to the minus 8 seconds. Okay. All right, so what I've done here is I've put the numbers that I made up for this radio wave, okay, 10-meter wavelength, and a period of 3.33 times 10 to the minus 8 seconds into this equation. So this equation becomes this equation. Then what I did is I graphed this in Excel. Okay, so I ran this over these times and over these distances to generate this wave. So what am I looking at here? Okay, obviously this is a function of z and t. Okay, so you have to fix either position or time and then vary the other. So what I've done here in this scenario, I'm saying, okay, at 0.5 seconds, let's look at the wave at various positions. Okay, so the wave at 0.5 seconds obviously is past 60 meters. Okay, so what is it saying? It's saying, well, at 0.5 seconds at position 0, the E field was 100. And again, all I'm doing here is I'm setting T here equal to 0.5. Okay, so that's just a number. Then I'm varying Z from 0 to 60 and I'm plotting it. Okay, so at 0.5 seconds, where is the wave equal to 0? Well, it's equal to 0 right here. Looks like at about, I don't know, 2 meters. That's equal to 0 here at 7 meters, equal to 0 again here at 12 meters, etc. Okay, so you can see the values of the electric field, at various positions given a time of 0.5 seconds. The next scenario I ran was, okay, now we're going to fix position, okay, at 10 meters. So we're going to sit at 10 meters and watch this thing oscillate through time. Start the clock at 3.33 seconds. It leaves the origin at time 0. So 3.1 period later, 3.33 times 10 to the minus 8 seconds later, what is going on at Z is equal to 10, okay? Well, that's where it's at its maximum. Again, that's 1 period later, right? It's its maximum again. Okay, and then we're just going to follow this thing over 5 periods or so. So that Excel graph is basically what we're looking at here, oscillating at a particular location as a function of time. The mathematical equation for the magnetic field is identical. It's just oscillating in a different direction. This is oscillating in the J or Y direction. E field, as you saw, is oscillating in the X direction. Okay, so how do we know that light is a wave and that it can be explained by these equations here? It comes from the work of the following physicists and mathematicians: Gauss, Faraday, Ampere, and Maxwell. Let's start with Gauss's law of electric flux. This law tells us that an enclosed charge, right, could just be a single electron, will provide for an electric flux through a surface, sphere, for example. Okay, so what is flux? Flux is just a measure of how much electric field is going through a surface. Mathematically, it's defined as the electric field, okay, the magnitude of the electric field times the area of the sphere, okay? And to the extent that this charge is centrally located, it would just be the electric field magnitude, be constant on all points of the surface if this thing were centrally located, times the area of the sphere. So again, it's a measure of how much electric field is penetrating some surface. And it's equal to the enclosed charge divided by a constant. That makes sense. The greater the enclosed charge, the greater the electric field and the greater the electric flux. This is just another expression for the enclosed charge, and it's the charge density times the volume. Gauss's law of magnetic flux tells us that an enclosed magnetic field will have 0 flux through an imaginary surface. So in this example, I have put a magnet inside of a closed imaginary surface, and we would measure 0 magnetic flux outside of such surface. Ampere's law tells us that a moving charge, which is a current, will induce a magnetic field in concentric circles around such current. Okay, so if you have a wire here with a current flowing through it, this would induce magnetic fields in concentric circles around the wire. Mathematically, it's represented like this. Okay, the magnetic field would be tangent at each point of this concentric circle, and if you add up the distance around the circle and multiply it by the magnetic field, assuming the magnetic field is constant every point from the wire, then that'd be equal to this constant times the enclosed current. That makes sense. The greater the current, the greater the magnetic field. The enclosed current can be modeled with this expression, which is the current density times that's the cross-section area of the wire. Faraday's law tells us that a changing magnetic flux will induce an electric field in concentric circles in a plane that is perpendicular to the changing magnetic field. So as you can see, the red arrows there are the induced electric field. Again, the X's are the direction of the magnetic field, and it's into page. And again, to the extent that it's changing, an electric field will magically show up. Maxwell's law of induction tells us that a change in electric flux induces a magnetic field. So it's just basically Faraday's law, except you replace magnetic flux with electric flux here, and the electric field, which was here in Faraday's law, replace that with the magnetic field. So if you combine Maxwell's law of induction and Ampere's law, you get this. Okay, so here was the law of induction. This is the magnetic field around a loop. It's equal to this, right? So that expression is here. And Ampere's law says the magnetic field times the distance of the loop, right, is equal to this. Okay, so we add that to here. Okay, so again, that's combining Maxwell's law of induction and Ampere's. Okay, the next thing I'm going to do is I'm going to convert these integral equations, and these equations all came from experiments, into differential equations. You'll find these conversion processes in most advanced books on electrodynamics. Before I do, let me just describe to you what this is. This is called a divergence. Okay, so del operator divided into a three-dimensional vector into Cartesian coordinates. Okay, so this is the operation. It's essentially a derivative in 3 dimensions. Curl's a little bit more complex. Okay, so the del operator, now we're going to use the cross product into a vector A with 3 components, x, y, and z. So it looks like this. If you want to know more about the divergence and the curl, check out this YouTube video. Give you kind of a conceptual overview as to what they are. Excellent video. Okay, so let's go ahead and apply first the Gauss divergence theorem, which basically says that the surface integral of a vector field f in this example, over a closed surface is equal to the volume integral of the divergence of a vector field over volume V. Okay, so again, this is a divergence operation. Okay, so all I'm going to do is I'm going to insert this equation which previously was demonstrated to come from an experiment, into this equation. Okay, and okay, so E dot ds, according to the Gauss divergence theorem, is equal to the divergence over this volume. Okay, so in this case, it's the divergence of the electric field. Okay, and we also know that this is equal to the enclosed charge represented by this equation. Okay, so let's focus on this equal to this. If these integrals are equal, then what's inside the integrals are also equal. Okay, so del dot E then must be equal to rho, dividing both sides by this constant epsilon. Okay, so this integral equation evolves to this differential form. Okay, applying the Gauss divergence theorem to the second equation, again, which came from an experiment. Okay, so we're going to insert B dot ds for this, and that's going to give us del dot B dV. Okay, again, this is equal to 0. So, so if the integrals are equal, then what's inside the integral is also equal. In this case, del dot B. If the integral del dot B dV is equal to 0, then del dot B must also be equal to 0. So this here evolves to this. Okay, next we're going to apply Stokes' theorem to the other 2 equations, again, derived from experiment. Okay, so Faraday's law. And when we do that, we're going to plug E dot dl in for this, and that's equal to the curl, right? The curl of the vector field. Okay, so E dot dl, again, I'm just going to go here, and that's equal to del dot E. Okay, again, using Stokes' theorem. And we also know that that's the rate of change of the flux. Okay, so if the integrals are equal, then what's inside the integral is equal, so this evolves to this. And finally, we're going to apply Stokes' theorem to the last equation, Let's go back. This equation, okay, and we get, so again, we're just going to plug this in for this, and that's going to give us del dot B, right? F dot dl is equal to del dot F, so B dot dl is equal to del dot B, all right, which we also know is equal to this expression here from the experiment. So once again, if the integrals are equal, then what's inside the integral is also equal. So del dot B is equal to mu j plus this expression, okay? So there you have it. From these four equations from experiment, we got these just by applying a mathematical operation. And this was derived by Gauss, and this was derived by Stokes. And you can find these derivations in most any vector calculus book. Okay, so this is where we are. What's next? Okay, so the next thing I'm going to do is I'm going to apply some vector calculus operations to these equations. So these were the equations from the experiment converted to differential form. Okay, if you don't know vector calculus, it's going to be confusing to you. But I'm going to go ahead and do it anyway. So what are we going to do here? I'm going to take the del cross operation. It's kind of like a derivative. A del cross operation of the left-hand side and the right-hand side of this equation. So if this is equal to this, then the del cross of this will also be equal to the del cross of this. It's kind of like if two equations are equal to each other, then their derivatives will also be equal to each other. Again, this is just more del cross. It's a little bit more complicated. Okay, so del cross of the left side and del cross of the right side. This becomes this. Okay, del cross of change of b with respect to t is the same thing as this. B here is just a vector calculus identity. Del cross E is the same thing as this. Okay, this is del dot E, so this is divergence. This is the Laplacian, the second derivative of E with respect to x, y, and z. Okay. Okay, so if we combine A and B, okay, we're going to get this expression here. Okay. Now, what I'm going to do here is I'm going to substitute the derivative of del cross B with respect to time. I'm going to substitute for that this expression here. Now, how am I going to get away with doing that? Well, you can see from equation 2 that del cross B is equal to the first derivative of E with respect to t. So if I take the derivative of the left-hand side with respect to t, then I got to do the same over here. So this becomes this. All right. So, and since I'm working in free space, right, the divergence of E in free space is equal to 0. So this equation becomes this equation. Okay, that is a wave equation. Okay, so the next thing I'm going to do, I'm going to basically do the same thing to this equation. So what I did here, I'm going to do it identically to the second equation. And that's going to give me another wave equation, but this time with respect to the magnetic field. So you have two wave equations. The second derivative of the electric field with respect to x, y, and z is equal to the second derivative of E with respect to t times this constant. Okay, again, same operation except with respect to the magnetic field. Okay, so from the experiments, these two equations evolve. These are wave equations again. All right, there they are. If you have an equation of this form, okay, I can prove mathematically and also from an experiment that the underlying function f is a wave. It's a model of a wave. Okay, and certainly that looks like a wave equation, right? And the velocity of such wave is v here. So what this is telling me then, okay, using this general form of a wave equation, that 1 over v squared is equal to mu e, this constant, which means that v is equal to the inverse of mu e square root, right? So if 1 over v squared is equal to this, then v is equal to this expression here. So we know these values from experiment, mu and epsilon. When we compute this, we get the speed of light.
So this was concluded in Maxwell that this oscillating electromagnetic field was light. And that was a miraculous moment for Maxwell, as it was for the human race. So a solution to this wave equation is this equation right here. Okay. And what I'm going to do is I'm going to apply 1 to it. So I've got the equation for the electric field. Okay, I know this is a solution to this equation. You can compute it. Take the second derivative of that electric field with respect to time, multiply it by this constant, and compare it to the Laplacian of the electric field, which is just the second derivative of this expression here. And I will get that will equal. So I know this is a solution. If that's a solution, you can set this here just tells us the magnitude of the wave at time equals 0, z equals 0. So you can actually eliminate that, and it's still a solution. But anyway, I'll leave it in for now. Okay, so what I'm going to do now, this is a solution to the wave equation for the electric field. I'm going to apply this operation to it. Okay, so del cross E gives me this expression here. Okay, so how do I know that del cross E is just changed in the x component of E with respect to Z? Well, here's del dot E. Okay, this wave, right, it's moving in the Z direction and it's oscillating in the X direction. So all of these others are 0, right? It doesn't have a Z component. It doesn't have a Y component, right? So that's gone. It doesn't have a Z component. That's gone. It doesn't have a Y component. It does have an X component, but it's not changing with respect to Y. It's moving in the Z direction. So del cross E is only equal to this term here. This is the only thing that survives from del cross E for this scenario I've created of an electric field oscillating in the X direction but moving in the Z direction. Okay, so I'm going to take the derivative of this equation with respect to Z, and I get this. Okay, that's a pretty simple operation. All right. And that's equal to dB dt, right? According to this equation 1 here. Okay, so now I want to derive the magnetic field equation from this. Okay, so I can use separation of variables here to solve for the magnetic field equation B. Multiply both sides by dt and then integrate. Okay, so that's what I've done here. I'm just going to integrate this with respect to time, and I get this. So integrating, just integrating the sine function with respect to time. Anybody that's had calculus knows how to do that. That gives me this equation here. Okay, and so this is a magnetic field equation. So this must be, right? This must be the amplitude, right, of the magnetic field. So k over omega times the magnitude of the electric field is equal to the magnitude of the magnetic field. Okay, so here you go. Here is the equation for the magnetic field right here. Okay, the next thing I'm going to do is I'm going to get a simplified expression for k over omega. I know that k is equal to 2 pi over lambda. It's already been discussed. Also know omega is equal to 1 over 2 pi times the frequency, right? So these 2 pi's cancel and end up with this expression here, 1 over lambda times f. Lambda times f is the speed of the wave. Okay, so k over omega is actually equal to 1 over the speed of light. Okay, so now I'm going to substitute 1 over c for k over omega, and now I get the amplitude of the magnetic field is equal to 1 over c times the amplitude of the electric field, which says that the amplitude of the magnetic field is really small compared to the electric field, right? It's just 1 over c times the amplitude of the electric field. Okay, so we're done. So what does this tell us? This tells us that the electromagnetic fields are in phase, right? They have the same angle here. They are in phase. So when this is at its maximum, this is also at its maximum. It also says that they are perpendicular to each other, right? The electric field is oscillating in the x direction. That was just a given. That was just made up. But this, which came from the experiments and operations, told me that the that that this is going to provide a B field in the J direction, right? So that's where that came from. So if I have an electric wave oscillating in the X direction, then the magnetic field must be oscillating in the J direction. J is another way of saying in the Y direction. This is sometimes expressed as I. So I is the same thing as the X direction. J is the same thing as the Y direction. So they're in phase. They're perpendicular to each other. Um, and what else? I think that's it.